is 2.3.1, the electric potential. In the last video, we talked about the fact that the curl of our electric field was always equal to 0. And that came from directly evaluating the fact that the path integral of a closed path within an electric field is equal to 0, which means that as long as I start and end in the same place, it doesn't matter which path I take to get there. They're both equal to 0. So I can write, not a closed integral anymore, but some path integral that goes from some reference point to a position that I care about. I can take that path integral through my electric field. This will not be 0 necessarily. This is going to be some single value that's going to depend on where I'm defining my reference point. Okay. I'm going to put a negative sign out front so I can make this definition. This is defined as the electric potential. All right, the electric potential is some path integral from some reference point to a particular point within an electric field. So it's a path integral. I can define the potential difference between 2 points that has nothing to do with my arbitrary reference point. I can call this V at point B minus my potential at point A is equal to, I'm just going to write down these definitions, some reference point to point B within my electric field, minus, but there's a negative sign, so it becomes a plus, from reference point, the same reference point specifically, dotted with my path. But I can flip the orders of these integrands. I will keep the first one the same. I'll go from my reference to B, E dot dl, right? And then I'm going to pick up a minus sign because I'm going to switch the order of my integrand. So I was originally going from reference to A. I'm going to go from A to reference. Let me write that more clearly. All right, but now the top and the bottom integrands of these two integrals are the same. So I can combine them into one single integral, which is minus E dot dl from A to B. We've seen this before. We can write this as an integral of the gradient of that potential dotted with dl from A to B, which therefore means that my electric field is negative the gradient of my potential. So if I know my potential, I can take the gradient. If I know my electric field, I can take these integrals and I can convert back and forth between them. All right, so something that's a useful thing to take advantage of is that we have in the past talked about having some electric field that is the sum of individual electric fields from components. That is also true for potentials, except now we can take a scalar sum instead of a vector sum. That makes our life a little bit easier. Okay, so let's do an example. This is example 2.7. Example 2.7 has a sphere. Okay, let's draw our sphere. Sphere of radius r, and it is a shell with a uniform surface charge sigma. I want to know what is the potential inside and the potential outside. Basically, I want to know the potential everywhere. All right. So we've done problems similar to this, if not the exact same problem before. We'll maybe instead of finding the potential, we wanted to find the electric field. Okay. So if I were to find the electric field, which I can take advantage of a symmetry to use Gauss's law, I can then use that electric field, integrate along some path, and then I'd have my potential. Okay. Specifically, this says to set the reference point at infinity. So ref at infinity. All right. So if I were to draw some Gaussian surfaces, let's do that. Different color. Gaussian surface inside of my sphere. Well, my sphere has no charges inside. It's just a shell. So if my Gaussian surface is less than or smaller than my sphere, for r less than r, that electric field is 0. Okay. I'm going to say that my surface charge density times my surface area is a total charge Q. And I draw my Gaussian surface bigger. I get that this is Q over 4 pi epsilon naught, 1 over r squared in the r hat direction. Put that vector there too. Okay, so if I want to calculate the potential, I need to integrate over the appropriate fields. All right, so let's do outside first. The outside for r greater than r. I'm starting outside because that's where my reference is. All right. I need to go from infinity to position r of E dot dl. And we mentioned before that this dot product doesn't matter about the path that we take. So I can take a really complicated path, or I can take the simplest possible path to some position r. Okay, I'm going to take the simplest path, which is a straight line. And I didn't draw that very well. I want to take the simplest path, which is just along the radial direction. So I can then choose dl here to be equal to dr r hat. That r hat dots with my electric field, infinity to r, 1 over 4 pi epsilon naught, q, 1 over r squared, dr. Okay. Can do that. We did that integral before. That's q over 4 pi epsilon naught, 1 over r, evaluated at infinity and r. I'm being sloppy about what's r in the integrand and what's r in the function. That becomes q over 4 pi epsilon naught, 1 over r. All right. So we notice something interesting about this expression. The potential decays as 1 over r, whereas the electric field decays as 1 over r squared. Okay, so we've done that. We found the potential outside. Now let's find the potential inside. I have r less than capital R. I must start from the same reference point to my position r dot dl. But now I need to break up my integral into two pieces because I need to have the electric field where it exists outside of this sphere being integrated over that path. And I need to integrate over the inside of my sphere where the electric field is different, right? I have a different inside and outside electric field. So minus infinity to capital R, or I know that my electric field is Q over 4 pi epsilon naught 1 over r squared. I'm going to do that same simple path, dr, and then I'm going to integrate from big R to my position little r, wherever that is, inside of my sphere. My electric field inside there is 0. All right, that integral is easy to do. That's not always the case, that second integral or secondary integrals cancel. And I'm left with the same integral I did before, except now instead of a little r, I have Q over 4 pi epsilon naught 1 over capital R. All right, this is a constant. The electric field everywhere inside of my sphere, sorry, the potential everywhere inside of my sphere is a constant. So if I were to plot the electric potential I have some constant value. Let's see if the bound, yep. So at the edge of my surface, these two are equal to each other, and then it decays like 1 over r.